A-level mechanics, the equations of motion involving constant acceleration. The SUVAT equations in 2 dimensions. Let's look at how we can use the SUVAT equations with 2-dimensional vectors. Now we've already seen that the SUVAT equations, that's the equations for constant acceleration, involve vectors, but usually we've been looking at it in the case when the vectors have been 1-dimensional. They can be 2-dimensional. We know that displacement, that's the letter S, the initial and final velocities u and v, and the acceleration a are all vectors. So we can write those letters in bold. T remains a scalar, and so that's not put in bold. Just to remind us, the equations are v equals u plus at, that's the equation where s is omitted. S equals u plus v over 2 times t, that's the equation without a. S equals ut plus a half at squared, that's the equation without v. S equals vt minus a half at squared, that's missing u. And v squared equals u squared plus 2as, that's missing t. Now, just to remind ourselves on some key points on vectors, we can write a vector, whether it's displacement, velocity or acceleration, in the form of a column vector, a over b, or an ij vector, ai plus bj, where a and b are the components of the displacement in the x and y directions respectively. Now we have position vectors always start at the origin. So if OB, that's 3i plus 4j, is a position vector, then B is the point 3, 4. If A and B have position vectors OA and OB, then the vector AB is the same as the vectors AO plus OB, so the vector AB is equal to OB minus OA. Example 1. A particle travels from A, which is 2i plus 3j, to B, which is 7i minus 9j, with constant velocity. In part A, find the displacement AB. Well, to solve this, AB is equal to OB minus OA, so that's 7i minus 9j, take away 2i plus 3j. That's 5i minus 12j. So AB is 5i minus 12j. In part B, we're asked to find the length of AB. Well, to begin with, we need to find the length of the vector AB, and that's equal to the square root of 5 squared plus minus 12 squared, which is the square root of 25 plus 144, or root 169, which is 13. So the length AB is 13. If the particle takes 5 seconds travelling, in part C, find its velocity. Well, the velocity is the displacement vector divided by the time. So that's 5i minus 12j all over 5, which is equal to 1i plus 2.4j. So the velocity is I plus 2.4j. In part D, we're asked to find its speed. Well, the speed is the distance divided by the time, and we know the distance AB is 13. So the speed is 13 divided by 5, which is 2.6. So our speed is 2.6 units per second. Example 2. A particle moves with constant acceleration. It starts with a velocity of 6i minus 3j meters per second and travels for 6 seconds with an acceleration of minus 2i plus 3j. In part A, we're asked to find its final velocity. Well, to solve this, we've got u equals 6i minus 3j, a equals minus 2i plus 3j, t equals 6, and we're trying to find v. So we can use v equals u plus at. Then, v is equal to 6i minus 3j plus minus 2i plus 3j all times 6, which is equal to 6i minus 3j plus, in brackets, minus 12i plus 18j. And that simplifies down to minus 6i plus 15j. So our final velocity is minus 6i plus 15j meters per second. Now in part B, we're asked to find its final position. So we need to find its displacement. Again, we've got u equals 6i minus 3j, a equals minus 2i plus 3j, and t is 6. This time we're trying to find s. So we can use s equals ut plus a half at squared. That gives us s equals 6i minus 3j all times 6 plus a half into minus 2i plus 3j all times 6 squared, which is equal to 6i minus 3j times 6 plus minus 2i plus 3j times 18, which is equal to 36i minus 18j minus 36i plus 54j. And that works out to be 36j. So our final position is 0.36. Although we've only been asked to find its final position, we could plot its position after each second. So we could plot its position for t going from 0 to 6. If we plot those values into the equation s equals ut plus a half at squared, we get, when t is 0, we get the point 0, 0. We can plot it. When t is 1, we get 5 minus 1.5, and we can plot that point. When t is 2, we get 8, 0. We can plot that. When t is 3, we get 9, 4.5. When t is 4, we get 8, 12. When t is 5, we get 5, 22.5. And when t is 6, we get 0.36, and we can plot that point. We can then join them up to draw the path of the particle. We could also see its final velocity, which is minus 6i plus 15j. So we can go across minus 6, up 15, and that shows its final velocity. Example 3. A particle starts at position 210 with velocity 2i minus 3j and acceleration 1i plus 2j. In part A, you're asked to find when it crosses the line y equals x. Now, when we try to solve this, the first thing we notice is it doesn't start at the origin. It starts at the point 2i plus 10j. We call the starting point S0. So we have S0 is equal to 2i plus 10j, u, the initial velocity, is 2i minus 3j, and a, the acceleration, is 1i plus 2j. We now use the equation s equals S0 plus ut plus a half at squared. This gives us s equals 2i plus 10j plus 2i minus 3j into t plus a half 1i plus 2j into t squared, which simplifies to s equals 2 plus 2t plus a half t squared into I plus 10 minus 3t plus t squared j. We can call this equation 1. Now, if the particle lies on the line y equals x, then the x-coordinate, that's the expression in front of I, is equal to the y-coordinate, which is the expression in front of j. So 2 plus 2t plus a half t squared equals 10 minus 3t plus t squared. If we double that, we get 4 plus 4t plus t squared equals 20 minus 6t plus 2t squared, which simplifies to t squared minus 10t plus 16 equals 0. Now that's a quadratic equation that we need to solve, but it factorizes. It factorizes as t minus 2 into t minus 8 equals 0, so t is 2 or 8. So we get for our answer, it crosses the line y equals x when t equals 2 or t equals 8. Now in part B, we're asked to find where it crosses the line y equals x. Now we can substitute both those values into equation 1. If we substitute t equals 2, then we get x equals 2 plus 2 times 2 plus a half times 2 squared, which is 2 plus 4 plus 2, or 8. If we substitute y, we get 10 minus 3 times 2 plus 2 squared, which is 10 minus 6 plus 4, which is also 8. If t is 8, we get x equals 2 plus 2 times 8 plus a half times 8 squared, which is 2 plus 16 plus 32, or 50. And y is equal to 10 minus 3 times 8 plus 8 squared, which is 10 minus 24 plus 64, which is also equal to 50. And so it crosses the line y equals x at 8, 8 and 50, 50. Now we could plot the position of the particle for each second. Let's draw a table. If t is 0, x is 2 and y is 10. We can plot this point. If t is 1, then x is 4.5 and y is 8. If t is 2, x is 8 and y is 8. If t is 3, x is 12.5 and y is 10. If t is 4, x is 18 and y is 14. If t is 5, x is 24.5, y is 20. If t is 6, x is 32 and y is 28. If t is 7, then x is 40.5 and y is 38. If t is 8, then x is 50 and y is 50. And if t is 9, x is 60.5, y is 64, and we can plot the last point. We can now join with a smooth curve. We can then draw the graph of y equals x. This is a straight line. This line crosses the curve at 8, 8 when t is 2 and 50, 50 when t is 8. In example 4, we're told an object is projected from the top of a 70-metre high building with a velocity of 1025. Assuming g is 10 metres per second squared, the origin is the base of the building, and I and j are the horizontal and vertical unit vectors. In part A, we're asked to write down an equation for s, the position vector of the object. Well, let's take up as positive, and then the first thing that we notice is the object does not start at the origin. It starts at 0, 70. So, we're given S0, the starting position, which is 0, 70, u, the initial velocity, which is 1025, the acceleration, 0 minus 10, and we're trying to find s for a given time t. So we're going to use the equation s equals s0 plus ut plus a half at squared. So substituting that in, we get s is equal to the vector 0, 70 plus 1025t plus a half 0 minus 10 t squared. Now in part B, we're asked to find when the object hits the ground. Well, we can write our equation as, in vector form, xy equals 0, 70 plus 1025t plus a half 0 minus 10 t squared. So we can say x is equal to 10t and y is equal to 70 plus 25t minus 5t squared. Now the object hits the ground when y is 0, so that's when 5t squared minus 25t minus 70 is equal to 0. And if we divide by 5, we get t squared minus 5t minus 14 equals 0. Now to solve that, we can factorise it. It factorises as t minus 7 into t plus 2 equals 0, which means t is 7 or t is minus 2. But t must be a positive number, and so our answer is it hits the ground after 7 seconds. Now in part C it asks, find where the object hits the ground. Well, we know t is equal to 7, and we know x is equal to 10t, so that means x equals 70. So it hits the ground 70 metres from the base of the building. Now note, we could plot x and y for values of t going from 0 to 7, in which case we get the table, t going from 0 to 7, then x goes 10, 20, 30, 40, 50, 60, 70, and y goes 70, 90, 100, 100, 90, 70, 40, 0. Now we can plot these points on the diagram and join with a smooth curve. This shows the trajectory of the object. Example 5. At 1 p.m. two ships, the Ariel and the Bothon, have positions 2016 and 213 and velocities -2, -5 and 4, -3 respectively, measured in kilometres. If they continue with the same velocities, in question A we're asked, at what time will the Ariel be due south of the Bothon? Now, the distance that a ship travels is the velocity times the time. So its end position will be its start position plus the distance travelled, so that's the start position plus the velocity times the time. So at time t, the vector OA will be equal to 2016 plus -2 -5t. And the position of B, OB, will equal 213 plus 4 -3 times t. Now we know BA equals OA minus OB, and so BA is equal to 2016 plus -2 -5t, take away altogether 213 plus 4 -3t. So we have BA is equal to the vector 18 -6t, 3 -2t. Now for Ariel to be due south of Bothon, the x-coordinate of BA must be 0. So 18 -6t equals 0, so t equals 3. So the time is 1 p.m. plus 3 hours, which means the time will be 4 p.m. In part B we're asked, how far apart will they be then? Now the displacement of A from B will be the y-coordinate of BA. That is 3 -2t when t is 3. So that is y equals 3 -2 times 3, which is -3. Now if the displacement is -3, the distance from A to B will be 3 kilometres. Now in part C, we're asked, what time will they be closest together? Let L equal the square of the length of the vector AB, in which case L is equal to 18 -6t all squared plus 3 -2t all squared, which is 324 -216t plus 36t squared, plus 9 -12t plus 4t squared, which is 333 -228t plus 40t squared. Now if we differentiate that, we get dl by dt is -228 plus 80t. So dl by dt is 0 when 80t equals 228, or t is 2.85. So t equals 2 hours 51 minutes. So we have a stationary point after 2 hours 51 minutes. But this will be a minimum, as the function L is an upright parabola, and therefore the turning point is the lowest point. So the time they're closest together is after 2 hours 51 minutes, which means the time they're closest together is 3:51 p.m. In part D, they ask how far apart will they be now? Well, we have L equals 333 -228t plus 40t squared, where t is equal to 2.85. So we have L is equal to 333 minus 228 times 2.85 plus 40 times 2.85 squared, which works out to be 8.1. Now the distance is the square root of L, so that's equal to 2.84605, so rounding it off, the closest distance is 2.85 kilometres.